So in continuation with our discussion about the application of Biot-Savart law, next let us apply the Biot-Savart law to find magnetic field due to a straight wire at a point. This is a finite size wire in which a current I is moving, and there is a point P nearby at a distance r from the wire in the plane of this paper. So wire is also in the plane and point P is also in the plane. And we have to find the magnetic field at this point because of this current. So let's say this is a wire like this and the point P is nearby. How is that we are going to identify this location of the point? The point P is at a distance of r. That means if I draw a perpendicular from this point to this wire, the distance of the perpendicular is equal to r. Further, the point P from the perpendicular makes an angle phi 1 on this side, and from the perpendicular makes an angle phi 2 on this side. This much data or information is sufficient to pinpointedly locate the location of the point P. We have to find the magnetic field of the point P. So wire and P are in same plane. We have to find the magnetic field of the point P. So using the Biot-Savart law, the first step will be to break this wire into infinitely small length dl, divide the wire into dl, find the magnetic field dB due to each cell dl. So what we are going to do here is that I have divided this wire into infinitely small length dl and I have to find the magnetic field at this point. So as per Biot-Savart law, dB will become equal to mu naught I upon 4 pi into dl cross r upon r cube. dl cross r will be a vector in direction of dl cross r perpendicularly downward. Now dl cross r will be equal to dl into r into sine theta. This is r in the numerator and this is r in the numerator, r cube. So it will become equal to dl into sine theta upon r square, and this dB will be downward for each of the dl. So if there is a dl here, dl cross r will be downward. If there is a dl here, dl cross r will be downward. If there is a dl here, dl cross r will be downward. So dB is downward direction for all the dl element, current element. So in this case, we don't have to do any vector addition because all the dB are already downward. We simply have to do scalar addition. Magnetic field will simply be equal to dB integral. This dB will become equal to mu naught I upon 4 pi into dl sine theta upon r square, where theta is the angle which dl makes with r. And this integral will become equal to mu naught I upon 4 pi is a constant. It will come out into dl sine theta upon r square. Here in this integration, there are three variables. Three variables means the things which are varying. What are the variables? dl is a variable, theta is a variable, r is a variable. For instance, if I take a dl here, dl1, the distance of the dl from the point P is r1, the distance of the dl2 from the point P is r2. This angle between dl and r1 is theta 1. This angle between dl and r2 is theta 2. So for every dl, both r1 is changing and r2 is changing, and theta 1 is changing and theta 2 is changing. Whenever there are more than one variable in an integration, we first have to reduce them into one variable, and generally it is the trigonometric variable we prefer. So we will prefer that all the variables will come in terms of theta. How is that we are going to convert them into one variable? By establishing the relationship between different variables. So what is the relationship? We can check out for the relationship from this diagram. If this angle is theta, this side is dl, then this angle is phi. We must have sine theta will be equal to cos phi, because theta plus phi is equal to 90 degree. Further, in this triangle L, this side L length upon r is equal to tan phi. Therefore, L will become equal to r into tan phi. Simply dl therefore will become equal to, what I have done, I have simply differentiated this dl will become equal to r into sec square phi d phi. And further, in this triangle, r by small r, capital R by small r is equal to cos phi. Therefore, small r, this distance small r will become equal to r by cos phi. I just put this value of r here in r square. I put this value of dl here in dl, and I put this value of sine theta equal to cos phi in this equation. I will get nu naught I upon 4 pi is equal to dl is equal to r sec square phi d phi. Then I put the value of sine theta equal to cos phi. Then I put the value of r is equal to r by cos phi. So r square will become equal to capital R square upon cos square phi. Cos square phi and sec square phi will become equal to 1. 1 r will get cancelled, and thus we'll have nu naught I upon 4 pi into cos phi d phi, which is a comparatively simple integration because the integration of cos phi d phi will be equal to sine phi. We just have to put proper limits such that we are able to include each of the section of the wire. That means I should be able to include this section also. I should be able to include this section of the wire also. How is it I am going to include this section of the wire? I have to put the limit of phi as equal to minus phi 2. And to include this section of the wire, I have to put the value of phi as equal to plus phi 1. Why minus phi 2? See, if this portion of the wire I have to include, I have to take phi to be equal to 0. Any length above it, phi will be positive. Any length below it, I have to take phi to be negative while putting it in the limits. Thus we have putting the limits nu naught I upon 4 pi r sine phi 1 minus sine minus phi 2, and the magnetic field because of a finite wire at a point P such that the point makes the normal from the point to the wire makes an angle phi 1 and phi 2 will be given by nu naught I upon 4 pi r into sine phi 1 plus sine phi 2. This is the result which we have to remember for solving many problems. So we have to discuss few important results that comes out from this formula. The first and foremost, the simplest case, this is a finite size wire. This angle is phi 1, this angle is phi 2. We have to find the magnetic field at this point. This distance of this point from this wire, if I draw a perpendicular from this point to the wire, is r. Magnetic field at this point will simply be equal to nu naught I upon 4 pi r sine phi 2 plus sine phi 1. What if the point P is here and the wire is here, such that, let us say this is the wire and the point P is here. Now the normal, if I draw a normal from the point P, it does not fall on the wire. If I draw a normal from the point P, the wire is not of that length so that the normal falls on this wire. This end still is given by this angle phi 1, and this end is given by this angle phi 2 from the normal. So I have to find the magnetic field at this point. Simply everything else will remain same, except that I just have to change the limits. To include this end, I have to take the limits as phi 2. To include this end, I have to take the limits as plus phi 1. If this is taken positive this time, this will also be taken as positive, and simply the magnetic field will therefore be equal to sine phi 2 minus this phi 1 is not negative this time, it will be positive, so magnetic field will become equal to sine phi 2 minus sine phi 1. Third case will be when the wire is of infinite length. So this is the point P, and the wire goes to infinity on this side and the wire goes to infinity on this side. If this wire continued to infinity on this side and to infinity on this side, this phi 2 will become equal to 90 and this phi 1 will become equal to 90. Simply what I have to do, I have to simply put phi 2 equal to 90 degree, phi 1 equal to 90 degree, to include the case in which the wire is of infinite length. Simply, the formula will become nu naught I upon 4 pi r sine 90 plus sine 90, and that will be equal to B into nu naught I upon 2 pi r. This is again a formula which we have to remember. So many questions are asked from this formula. So, for an infinite wire, magnetic field at any point nearby at a distance of r from it will become equal to nu naught I upon 2 pi r. This magnetic field will be perpendicular to the plane of this wire. If the current is going upward, the magnetic field will be going inside this plane. This we get from the Biot-Savart law from the direction of dl cross r. What if the wire continues to infinity on one side and starts from just in front of the point P? So this wire starts from this point and it goes to infinity on this side. What will be the magnetic field in this case? Simply, we just have to change the limit. This angle phi will still be equal to 90 degree, whereas this angle now will become equal to 0 degree. So, in the same formula, nu naught I upon 4 pi r sine 90 plus sine 0, it will become equal to nu naught I upon 4 pi r. And if the current is going downward, the magnetic field in this case will be perpendicularly upward. Do remember that because of every portion, the magnetic field at this point will be either perpendicularly downward or perpendicularly upward. So we will discuss one more case. This is again a finite wire at a point symmetrically placed. The point P is symmetrically placed, that means in between the two wires at this point, so that this length is equal to this length. Let us say this length is equal to L by 2, this length will also become equal to L by 2, and this distance is R. This angle will be phi, this angle will be phi. We simply have to apply the formula. B is equal to nu naught I upon 4 pi r into sine phi plus sine phi. This angle is phi, this angle is phi, and that will be equal to nu naught I upon 2 pi r into sine phi, where sine phi will be equal to this side upon this side. This side is L by 2, this side will be equal to L by 2 whole square plus r square under root. So same formula we have to apply in different, we can apply in different cases to find the magnetic field. Next case, let us say the wire is straight and the point P is such that it is along the line of the wire. What will be the magnetic field because of this wire at the point P? Answer is magnetic field will be equal to 0. If the point P lies along the wire. Why? Because for every such dl will be in this direction, r will be in this direction, dB will become equal to 0. We know that dB and r in that case will be parallel to each other if the point P is along the line of the wire. Thus dB will become equal to nu naught I dl cross r, and dl and r are, because they are parallel to each other, magnetic field will become equal to 0. This is what is shown here. dl and r are both parallel to each other. Each of the dB will become equal to 0. Their sum of all such dB will also become equal to 0. Now, we can find the direction of magnetic field at any point because of a straight wire, either by Biot-Savart law, or we can now develop a general rule to find magnetic field, and that is the right hand rule. What do we do is, if the wire is straight, we point the thumb in direction of current, at any point along the wire, and curl the right hand. The fingers will point at any point in the direction of magnetic field. Fingers curl in direction of field. This is different from the magnetic field for a curved loop. What we were doing there, we were curling the fingers in direction of current. For a current loop, we do just the opposite. We curl the fingers in direction of current, and the direction of thumb there points in direction of magnetic field. Whereas for a straight wire, If I want to find the field because of a straight wire at any point, I simply have to take my thumb along the direction of the wire and curl the finger. So at this point the finger will be pointing perpendicularly downward. So magnetic field in this case will be perpendicularly downward, whereas at this point the fingers will be pointing perpendicularly upward. Magnetic field at this point will be perpendicularly upward.